Welcome to Probability and Statistics. In this lecture video, we're going to talk about approximating a binomial distribution using a normal distribution. Now, as you can recall, the binomial distribution in lecture video 5.2, where we use the binomial CDF or the binomial PDF to find the probability. Now we can actually use normal distribution to approximate binomial because the binomial can actually become a bell curve shape, just like a normal distribution. So as the number of trial increases, my picture here shows that as the number of trial increases for the binomial distribution, this picture A here is number of trial is 10. This one is number of trial is 30. So as I increase my number of trials, eventually, okay, my binomial distribution will look more and more approximately normal. So what we're going to try to do in this lecture video is learn how to use the normal CDF, okay, to approximate the binomial distribution. All right, so here is a quick formula. You probably remember this. All right, if the condition that n times p, as you can recall, n means number of trial, p means probability of success, and n times q is also greater than or equal to 5, then a normal distribution can be used to approximate a binomial. Alright, so n times p, as you can recall back in lecture video 5.2, excuse me, it's 5.2. Alright, n times p is how we find the mean for the binomial distribution. N times p times q will be our variance, sigma squared. So to find the sigma, we take a square root. Alright, so make sure you find this on the formula sheet. Now, before I do any example with this, I want to talk to you a little bit about this thing called the continuity correction. Continuity correction. It's a correction factor used to convert a value of a discrete random variable to an interval range of a continuous random variable. So when we need to convert from discrete to continuous, okay, this thing is called a continuity correction. So as you can recall, if I have at least, for example, if I have at least 45 or more, my symbol is greater than or equal to 45. Alright, so under the binomial distribution, okay, greater than or equal to 45, I will probably use binomial CDF, and 1 minus the binomial CDF will give me what's to the right side of 45. Alright, so with the continuity correction, rather than use 45, under normal we will use 44.5, because as you can recall, okay, the normal curve comes from a histogram. A histogram is a rectangle. So let's pretend our rectangle is about this height. I want to go back here. If you notice the x-axis, on the x-axis, all these numbers are located at the center of each rectangular bar in my histogram. Alright, so let me make this a little bigger. I'm gonna do it down here, okay? Let me do it on a different page. Alright, 45. Let me go to a different page. Let me show you this. Just gotta remember it. Alright, so let's say here is a histogram, one of the histograms. The 45 they're referring to is right here. I need to find the area to the right if I want to find the area to the right of this thing, everything to the right. Alright. So that means what I want is right here. But that actually does not cover the whole rectangle. This is only half of a rectangle. So for me to cover the other half, okay, under the normal distribution, remember I mentioned under normal you cannot actually find exact 45. So instead of using 45 under the normal curve, we will use this number 44.5, just minus the 0.5, because that will actually give me the other half. Okay, give me the other half of rectangle to the right. So that means this line is where I want to start going to the right. Alright. And that's what this picture is trying to say. So greater than equal to, we will use 44.5 to the right. Alright. If it says greater than 45, just want to be greater than 45. That should make sense. If I want to be greater than 45, let me go back. If I want to be greater than 45, that means I don't even want this right hand side of where my 45 is. If I want to be greater than 45, I got to come up, use 45.5, and then to the right. Okay, that makes sense, because greater than 45 means you do not include 45. So that means you do not include the area of the half of that rectangle where the 45 belongs to. So we're going to come out to this line, 45.5 to the right. Alright, if it's less than equal to 45, less than equal to 45, that means what I want is to the left side of 45. But if I do to the left of 45, that means there's another half of a rectangle I'm not including. So that's why again I got to use 45.5 to the left. Everything to the left of 45.5 will actually include this entire rectangle. So there's a, so these 0.5 thing is my continuity correction. This is how we go from discrete to normal. Less than 45, that means 45 is not even going to be included. Less than 45. So if 45 is here in the middle, I want to be less than that. So that means I cannot include, okay, this side of the rectangle. So that's why I got to start at 44.5, then to the left. That's what I want. So if I want to find exactly 45, normal CDF, you can't really find exact answer. Okay, so if you want to find exactly 45, then what we got to do is we got to go from 44.5 to 45.5 for that entire rectangles area. Just that rectangle area. It doesn't include anybody else outside of it. So exactly 45 means I just want to find the area under the curve for this rectangle. Because remember a normal curve. Where's my picture? Let me show you right here. Alright, a normal curve. Under the normal curve, this is actually not exactly a rectangle, because rectangle is actually under the curve. So for me to find that tiny little piece with the area that's under the curve along with my rectangle, okay, we have to, we can use normal distribution to approximate it. So just to find the area in between, to find exactly 45, I got to go from 44.5 to 45. Alright. So we'll keep this in mind, okay? Keep this in mind. We'll come back to some of these examples. Now for right now, I want to quickly do an example of the mean. Okay. And let's see if we can follow this formula. So the condition n times p gotta be bigger than or equal to 5, and n times q gotta be bigger than or equal to 5 for us to use the normal distribution to approximate the binomial. Alright, so let's take a look. Consider the probability that at least 18 out of 143 DVD will malfunction. Assume the probability that a DVD will malfunction is 1%. Specify whether the normal curve can be used as an approximation to the binomial. Verify the condition. Alright, so if I need to verify the condition, that means first of all, my mean, which is n times p, got to be greater than or equal to 5. So my n, number of trial is 143 times probability of success. 1%. Our success here is actually malfunction, 0.01. So that will actually give me 1.43. So this is not greater than 5. Alright. Let's look at the other condition. N times Q gotta be bigger than or equal to 5. N times Q. Q is probability of failure. So that will be 143 times, well, probability of success is 0.01. Probability of failure got to be 0.99. So 143 times 0.99 is 141 something. So that is greater than or equal to 5. Alright, but if you read this thing carefully, if you read this formula carefully with the word and, so that means both of these conditions, both of these got to be greater than or equal to 5 for me to use normal distribution to approximate. So, can we use normal curve to approximate? The answer would be no. And the reason is, when I do n times p or when I do n times q, one of them is not greater than 5. Alright, so the answer would be no. Alright, let's consider the probability that more than 92 out of 157 flight will be on time. Assume the probability that flight will be on time is 62%. So when you read this problem, you have a sense of this is a binomial distribution because either the flight will be on time or not on time. So approximate the probability using a normal distribution. So the problem is telling me to use the normal distribution to approximate the binomial. Alright, so let's write down what we know. Then we can use the formula. So we're gonna piece this thing together, okay? Because right now, how do I use normal to approximate binomial? Well, first thing first, when I use normal CDF, I'm gonna put it down here, okay? When I use normal CDF from the previous lecture video, I got to type in the lower bound, the upper bound. Mean is 0 for the normal curve, standard deviation at 1. And my lower bound and the upper bound are the z-scores. Okay, so that means I got to find z-scores. So for me to find the z-score, as you can recall, from our previous 2 lecture video, or previous 3, how do I find the z-score, which is this formula right here. So I need to find the z-score for me to put either lower bound or upper bound. Just to find the z-score, I got to have a random variable x, a mean, and a standard deviation. So that means I need to actually find the mean and a standard deviation for this problem first before I can convert it into a z-score. Okay, so with all 3 things in mind, alright, let's write down what we know. My n, number of trials, there are 157 flights. Alright, my p, probability that it will be on time, 0.62. Q, probability of failure, not on time, 62% on time. That means 38% is not on time. Alright, so let us find the mean. So I got these 2 formulas in my mind. I'm going to put this on the side, okay? So the mean will just be n times p, 0.62. 157 times 0.62. So the mean is about 97.34. Okay. So normally out of the 157 flights, on average about 97 flights will be on time. Alright, standard deviation, which is square root of n times p times q, 0.38. Just to be more accurate on my answer, I'm actually just gonna leave this like it is, okay, when I put into this formula, because I don't want to do any rounding in the middle of my process. So now the z-score. What is my random variable x? Well, it says more than 92 flights. More than 92 flights. So I don't want 92. So more than 45 was 45.5. So now it would be more than 92. More than 92, that means I gotta what? Use 92.5. Okay, like I explained earlier. So my z-score, my random variable x will be 92.5. Starting from 92.5, going to the right. Alright, excuse me. Minus the mean, 97.34, divided by this big old standard deviation. Now I would put all that in the calculator at one time. Alright. Let's see. Round to 2 decimal place. So what I'm going to do is subtract first. And the top is negative 4.84. That makes sense. 92.5 is to the left of 97. Divided by second square root, and inside the square root I will type in my 157 times 0.62 times 0.38. Then I run to 2 decimal place. So that's about negative 0.80. All right. So now, since I want to find the area to the right, that means I will start at the lower bound, negative 0.80. Upper bound, keep on going to infinity. That will be 1e99, comma 0, comma 1. So second distribute, number 2. Negative 0.80, comma 1 e99, comma 0, comma 1. So the area to the right is about 0.7881. All right. If I use the actual binomial CDF to the right of 92, that will be 1 minus second distribute binomial CDF, because I'm counting from 0 flight will be on time all the way up to 92, because I want to be more than 92. So I'm not even going to count 92 as what I want. It's 93 flights and up. So binomial CDF, what do I type inside the binomial CDF? Number of trials, 157, comma. Probability of success is going to be 0.62, comma. The number of success, more than 92 means I will put 93. Typing around, Lord. So again, binomial CDF. No, 1 minus, because I need to find the area to the right, so I gotta do 1 minus 157, comma 0.62, comma 93. So 93 to the right is what I want. Oh, so 92, excuse me. What I don't want is 0 flight on 10 all the way to 92. So once I figure out what I don't want, subtract it from 100%. Okay, that's very, very close. 0.7876. 7876. Okay, so normal distribution can be used. It can be used to approximate your binomial. All right. Let's try another one. I think this one is fewer than 18 flights. Fewer than 18 flights. So fewer than is less than. Okay, less than here. So fewer than 18. I don't use 18. I use 17.5 instead. Alright, so let's see what do we know. My random variable x fewer than 18. So now I will use 17.5. Alright, number of trials, 146 flights. Probability of success, which is called delay in this example. The chance of delay is 0.08. Not gonna be delayed. 0.92. Alright, so again, just like the previous problem, gotta find my mean standard deviation before I can put it into the z-score. So my mean, n times p, 0.08. So the average delay out of the 146 flights is about 11.68. Alright, my standard deviation. Again, I'm just going to write it out. I'm not going to type it in yet. 146 times my P times my Q. Alright, so let's do my Z-score. Alright, fewer than 18, we will use 17.5 instead of 18. The mean minus the random variable x minus the mean divided by the standard deviation, which is all that stuff. So all I'm gonna do is just type that in. Put it right there. 2 decimal places. So I'll subtract first. 5.32 divided by second square root times 0.08 times 0.92. 1.62. Alright, so this time I'm looking for fewer than, okay, it's area to the left. So how left do I go? Negative infinity. So my normal CDF will be -1 E99, comma, all the way up to my upper bound, 1.62, comma 0, comma 1. So the area to the left, 0.9474. Type in the square root of 146. Okay. Alright, so we'll assume the probability that a given flight will be delayed. Alright. So what's the probability that fewer than 18 plane will be delayed? Fewer than 18 will be delayed will be about 94, almost 95%. Alrighty. Now let's do one with the word exact. So when we do exact, in this picture, exact got to be from the 0.5 to the left to the 0.5 to the right. So consider probability that exactly 96 out of 149 people would not get flu this winter. Assume the probability that a given person would not get a flu is 58%. Alright, so exact 96, that means I gotta use 90. I gotta use 95.5, and I gotta use 96.5. Okay. Alright. So let's see, what else do we know? Number of trial, 149 people for example. Okay, that's my sample size. Probability that will not get a flu, 0.58. So the probability that it will get a flu, 0.42. Alright, so my mean was my average of people that will get flu. N times P would not get a flu. If you put this in a calculator, 149 times 0.58, 86.42. Alright, standard deviation, plus or minus so many people will not get a flu. That'll be 149 times 0.58 times 0.42. Alright, let's find the z-score. So I'm looking, so the word exact will make me look in between, the area in between 95.5 to 96.5. So I gotta do this thing twice so I can find my lower bound and my upper bound. So the z-score for the 95.5 minus the mean divided by the standard deviation, which is this big old thing right here. Put my C back in there. And then the other one will be the same thing, just using 96.5. Show you a quick way to do this. So you see how earlier when I type in the calculator, I subtracted first. So this time I'm going to let the calculator subtract the top first by putting 95.5 minus the 86.42, close a parenthesis. Now I will divide it by the square root of 149 times 0.58 times 0.42. And the reason why I'm doing it this way, typing it this way, is so in a minute I can just copy what I just typed. 1.51. Alright, check it out. That's the z-score. So now, second entry, it reprint what I typed earlier. So all I gotta do is go back and change the 95.5 to a 96.5. Now give me 1.67 for the z-score. Alright, so that's my lower bound, that's my upper bound. So normal CDF (1.51) to 1.67, comma 0, comma 1. Okay, what's the chance? Exactly 96 people out of the simple 149 will get the flu. Will not get the flu. .0181. About 1.8% chance they would not get a flu. Alright, so just want to show you how we can use normal distribution to approximate binomial. Alright, that will conclude this lecture video. Thank you for watching.